Jack received his BS in math from MIT and his PhD in applied math from UC Berkeley. He was a member of the astronomy faculty at the State University of New York, Stony Brook from 1987 through 1996. And he's been a research scientist at NASA Ames Research Center ever since. He is also, I believe, a consulting professor in Stanford's Department of Geological and Environmental Sciences. And he's a co-investigator on the Kepler mission. And today he'll be telling us all about the formation of giant planets.
Very good. Thank you, Cynthia. 100% correct. It's a pleasure to be here. I'll enjoy being on your side of these talks, and so I'm happy to have a chance to give one of my own. And I'm going to be talking about some work that I've recently completed together with three colleagues, one of whom, Gennaro D'Angelo, is in back here. And I'm going to put it in context. It's recent work on models of giant planet formation. And I want to give you context in the sense of tell you a little bit about giant planets, what they're like, because that's what we use as clues to our understanding their formation, then give you a broad brush on formation models, and go on to give you some of the latest, most interesting or most exciting results. So we have in our solar system a lot of information about the giant planets. Now, the giant planets, we believe, form together with the terrestrial planets and smaller objects, so they're also relevant. We know a lot more about the giant planets in our own solar system. Even though there are only 4, we have a lot more data on them than we do on the 300 or so planets, giant planets that have been detected around other stars. We have information from observations of young stars, of disks, which appear from both observational and theoretical considerations to be forming those stars. And all these data are important inputs into the models of how planets formed. So I want to tell you a bit about planet formation in general and terrestrial planet growth as just a little prelude to giant planet growth, since they're closely related, and then talk about the different models of giant planet formation, because there are a wider range of models of giant planet formation being worked on today than models of terrestrial planet formation. And then I'm going to focus in on the core accretion gas capture model, in which a giant planet forms in its initial stages in a manner like a terrestrial planet forms, by the agglomeration of solid objects, and then becomes massive enough that it starts capturing a large gaseous envelope, predominantly hydrogen and helium, the two most cosmically abundant elements. So I'll give you various details on some of our new results and conclude by putting things back in perspective. So looking at our solar system, not in the detailed way that you do, many of you do in your research, but in a broad brush way, things that we can try and put together to understand how planets form. Now, planetary orbits are Keplerian ellipses, aside from slight relativistic and corrections and perturbations upon one another. And that's physics. That's just the laws of physics. That doesn't tell us anything about how the planets formed. But there's nothing that physics by itself says without additional input that would explain why the orbits of the planets are nearly circular and coplanar. If you look at binary star systems, the eccentricities get very large. And in fact, extrasolar planets that have been seen now generally have fairly large eccentricities, except for the close-in ones whose orbits are tidally damped. And the orbits, none of the planets in our solar system are close enough in to have tidally damped orbits. Moreover, planetary orbits are nearly coplanar. Solar system is quite flat, except for the small bodies. And we believe that this is another clue to the fact, or to what we believe to be the case, that the planets formed in a disk around the young sun. The spacing of the planets increases with distance from the sun. Now, there is some physics behind this in the sense that if planets are too close to one another, they will perturb one another into crossing orbits, and they'll either collide and accrete or disrupt, or one will be tossed out of the system or into the sun or something like that. And proximity in this case is typically measured by the ratio of distance of one planet's orbit to another, one planet's orbit from the sun to another planet's orbit. And that's because if you look at the relative magnitudes of the gravity of the sun giving the dominant Keplerian orbit and the perturbing effect of the other body trying to move it out and to bring things into crossing orbits, this is the relative positions. Now, there are other factors involved. More massive objects perturb one another more strongly. And if you're closer into the star, closer into the sun in our case, you go around, you orbit much faster, and therefore the system has to be stable for a longer dynamical period, a larger number of orbits to still exist. Another clue is that if we look at the giant planets, the objects with a lot of gas, and they all have satellite systems. And indeed, the inner satellite systems of all the giant planets have nearly circular and coplanar orbiting moons. In those cases, the circularity is actually could be the result of tidal forces because the satellite systems orbit close to the planets, but the coplanarity not. So that's the dynamics, key dynamic aspects. Now we look at what the bodies are made of. The largest bodies are the most gas-rich. Indeed, the sun has the largest fraction of hydrogen and helium, over 98%. Jupiter, maybe 90% roughly, maybe a little more, a little less hydrogen and helium. Saturn, about 75%. Uranus and Neptune, about 20% or so. And all the smaller objects, just trivial amounts. And I'm not counting the hydrogen in the ices, but that's fairly small by mass. And among the Condensed objects. You got rocky bodies near the sun, ice-rich bodies, ice rock bodies farther out. That suggests condensation has a role. Cold enough to condense things far from the sun. Ice is far from the sun, close in, only more refractory material condenses. There's a great deal made of variations in elemental and isotopic abundances in meteorites. And that can be very important in a detailed sense. But the gross picture is that things are very uniform aside from the fraction of volatiles, which tends to increase with distance from the sun, but there are exceptions there. Now, while composition of meteorites are actually very similar to that of terrestrial planets, other than volatile content, which vary among meteorites, if you look at a meteorite on small scales, and thinking in both the compositional and the structure cases, the primitive meteorites, the objects which have not melted since they agglomerated back when the solar system was young, they're very, very heterogeneous. On centimeter scales, look, huge variety, different compositions of different grains, inclusions, etc. And that means things were very active. Some things were heated to high temperatures within the protoplanetary disk, whereas some interstellar grains which would have vaporized at those temperatures are still extant. Now, planetary geology also provides clues to the origin, and that's primarily from the cratering record, which has been dated on the moon, the major scientific result of the Apollo missions. And that says that the surfaces, which are about 80% the age of our solar system, have over an order of magnitude fewer craters than surfaces that are about 95% the age of the solar system. That means the cratering rate has dropped substantially. There was a lot more junk out there when the solar system was young than it is today. There is today. Now, you have pictures, you've all seen pictures showing comparisons of the planets. But when you see the standard 2D pictures, the giant planets are bigger. The great red spot is bigger than the Earth, you know that. But this perspective, which gives you a bit of a 3D view, really shows you just how different in volume the giant planets are from the terrestrial planets. And this is partly because the giant planets are substantially more massive. 318 Earth masses, 95 Earth masses, 14, 17. But also because the giant planets are fundamentally different objects in the sense that they have substantial amounts of hydrogen and helium, the lightest elements, and they're in gaseous form, and so their densities are lower than the terrestrial planets, despite the fact that they have more material and therefore much greater compression. Jupiter's not that much bigger than Saturn, even though it's 3.5 times as massive and made of, on the average, denser stuff just because there's a lot more pressure and the hydrogen and helium is higher density in most of Jupiter. Now, they're giant planets, but the sun is still huge. Much more massive, 1,000 times as massive as Jupiter. A lot more pressure, and not that different in composition, but the pressure is so great that the temperature at the inner part of the sun is large enough for hydrogen to fuse into helium, tremendous heat source, and it's the thermal energy which keeps the sun as big as it is. And that thermal energy is radiated out, but it's balanced on 10 billion year timescales by nuclear fusion until the hydrogen in the core will run out. So, a few images of our giant planets. This is Jupiter and the two inner Galilean satellites, Io slightly larger than our moon, Europa slightly smaller, Saturn viewed by Hubble, various seasonal changes. Hubble views of Uranus and Neptune, they're actually pretty bland and don't look like they have a lot of features. They don't look very different from one another in these images. But if you enhance the contrast, then you see different features. Incidentally, Voyager had very different images of the two planets, and that's because at that season, Uranus was pointed very differently. Uranus was near the summer solstice, whereas Uranus here near the equinox, and a different part was being observed because different part was lit in the sun. Uranus is tilted on its side. Neptune had a lot of features, and Voyager could see features better because it was closer. So we really want to know, if we want to understand how these objects were made, what they are made of. With Uranus and Neptune, they're mostly heavy elements, things heavier than helium. And therefore, actually there's an uncertainty of about a factor of 2 in the amounts of hydrogen and helium in these objects. But they're a small fraction of the total mass of these objects, and therefore the solid, the heavy element component is not very uncertain. And it's clearly concentrated towards the center. The hydrogen and helium are on top as part of the envelope. Some may be mixed into the core, that's uncertain. But in the case of Jupiter and Saturn, they're clearly enhanced in total heavy elements. Jupiter would be around here in total heavy elements. Saturn would be around here if they were solar composition. But it's not clear how much of these heavy elements is in the core, concentrated towards the center, and how much is mixed through the envelope. Same is true for Saturn. And the problem is that a lot of the hydrogen and helium, especially in the case of Jupiter, is at megabar pressures, and the equation of state of hydrogen and helium mixtures at those pressures is not well known, and hydrogen and helium are the dominant constituents, so little uncertainties translate into big uncertainties in heavy elements. Circumstellar disks. We observe them. This is an image, coronagraphic image of the Beta Pictoris disk, the most photogenic because it's bright, it's nearby, and we see it almost edge on. It's a second generation disk of debris from collisions of probably asteroid-like objects or comets. But they're parent bodies because the dust that we're actually seeing there would not survive for the age of the star, which is 10, 20 million years. Low in mass, this dust could be a few lunar masses. There's not much gas relative to heavy elements in these disks, and they're more prominent around younger stars. They're just remnants, and they're showing that systems that are flattened are produced. Young stars, evidence of disks, infrared excess, rotation of gas. There are images that HST has seen. Radii of the disks are 10 to hundreds of AUs for solar mass stars. Typical mass are a few percent that of the star. The lifetime, and it's the dust that's seen in most of these cases, is typically a few million years for these massive disks. You still have these remnant disks around older stars, but disks that are massive enough to form planets last only for typically 3 million years, in some cases up to 10 million years. And you could hide the solids by forming planetesimals, by growing to bigger bodies. But the gas, that's hard to hide. And if you have gas, it's hard to get rid of the dust. Hard for it to all form into planetesimals or be lost. And there's some structure, gaps, inner holes, which could be caused in these disks, which could be caused by planets. Here are some of the proplids. Here are infrared images of the star-forming regions showing disks, showing a lot of dust. And it's just a case where a star is, let me go back. Stars form from the collapse of molecular cloud cores. Those cores are about 10 to the 5th times the size of the stars in radius. If you collapsed over this factor of 10 to the 5, if everything fell into the star, the moment of inertia goes as a square of the radius, so it would go down by a factor of 10 to the 10th, 10 billion. Conserve angular momentum, you'd have rotation going up by a factor of 10 billion. Even a slowly rotating core, 10 billion. That would mean it rotating so fast that it would be swirling things out like crazy at the equator, centrifugally unstable. You can't get it that far in, so the collapse goes down. The material with the least angular momentum goes into the star. That with the greater angular momentum wants to go as close to the center as possible, but it needs to retain that angular momentum, and that's why you get a star plus a disk. So, looking beyond, let's take a look at the extrasolar planets, because they give some of the most exciting data we have. Now, there are various techniques. Pulsar timing was the first to succeed, but haven't seen many planets that way because it only works on these dead stars, and those planets probably formed in a situation very different from our solar system, or at least very different from the environment in which giant planets form in our solar system. Radial velocity, or Doppler method, has been successful. The vast majority of known planets have been found with the Doppler method, which just measures the orbit, the component in our direction, the speed of the orbit of the star around the planet, because they're both moving around the mutual center of mass. Astrometry is just measuring the other two components of the motion of the star in response to the planet's gravity on the sky. It's been the great hope for, well, since well before I was born, for finding planets around other stars, and someday it may work. Transit photometry, observing planets going in front of their stars periodically as they orbit, has been very successful in the last few years. Several dozen planets have been detected, and as Cynthia said, I'm a co-investigator on the Kepler mission, which is scheduled for launch from the Cape on the evening of March 4th, 2009. And that will detect planets smaller than the Earth, including true Earth analogs if they are fairly abundant around other stars. Right now, transit photometry has only detected giant planets, or only discovered giant planets. There was one Neptune-like planet detected after its discovery with radial velocity. And there's some other methods. I'm not going to go into details on these because they haven't yielded clues yet, but just want to let you know that there are other methods being pursued, and they're going to give us more information on other planets. Now, what have we been seeing? This is a histogram in factor of 2 mass bins of planet mass, of planets detected by radial velocity. Not actually planet mass, but this is the minimum mass, m sin I, because if the orbit is tilted, the plane of the orbit is tilted towards the line of sight to Earth, then the motion of the star is largely out of the plane, not into the direction that we see its velocity. So the minimum mass is what it would be if the orbital plane, the line of sight is in the orbital plane. If the orbital plane is tilted relative to the line of sight, you need a bigger mass of the planet to have the same component of the radial velocity, that which we see, same component of the velocity viewed as radially from Earth. Now, there's a peak here between 1 and 2 Jupiter masses. You have a drop-off for larger mass and for smaller mass. But it's difficult to observe these planets, and smaller is more difficult to observe. Some stars you have better precision. It's also more difficult in radial velocity to observe planets farther from their stars because they don't have as much of a perturbation and it takes longer for the signal to build up. So there are a lot more chances of observing the more massive planets than the low mass planets. This drop-off is real. And in fact, the real drop-off has got to be steeper than this, because as you go to the left, they're more difficult to detect. So whether this drop-off is real, we don't know. Excuse me. The statistics here are a pretty small number, but there should be a significant drop-off here, and there's not. There's this sign of a dip. And that suggests that these planets are really rare, because the real ratio is probably not 9 to 6, which is not statistically meaningful. But to give this type of ratio in observed objects, it may be, say, 29 to 6. And this is in the between, a little larger than Neptune and around Saturn. There seems to be this paucity. And there's definitely a drop-off beyond Jupiter. Now, if you look at the stars and look at the spectrum, you can estimate the abundance of heavy elements in the stars. This is the abundance of heavy elements. It's on a log scale. Over here, we're talking about 3 times as much heavy elements in the planets, in the stars as in the sun. Here, 1/3 as much. And the more metal-rich stars have a much, and the sun is here. More metal-rich stars have a greater abundance of planets. And in this case, we're talking about giant planets orbiting within a few astronomical units of the sun. So the fact that the sun only has about 4% or so, would be expected to have 4%, well, the sun doesn't have any planets like this. But it is interesting that these, talking about Jupiter mass planets, so they're probably mostly hydrogen and helium. The ones we've seen in transit certainly are mostly hydrogen and helium in the Jupiter mass regime. And yet, their abundance is strongly correlated with the amount of heavy elements in the stars. This shows radius versus mass. It's kind of an interesting plot. Now, these are only transiting planets. Otherwise, we wouldn't have the radius. And most of them are orbiting very close to their stars. And some of them are actually so big that if they're cold like Jupiter and pure hydrogen and helium, Jupiter's a little under pure hydrogen and helium, so is Saturn, because they have heavy elements. They would be smaller than they are. They've got to be heated. So this is kind of lower limits on what their kind of honest size, cold size would be. So the 2 objects that are most interesting are this guy, HD 149026b, a transiting planet, which is a little over 100 times the mass of the Earth. When we get the transit, we get actual masses, not just m sine I, because we know the inclination of the orbit. So it's a little more massive than Saturn, and it's smaller in radius than Saturn. And that means it's got to be mostly, a little over half, heavy elements. And that means over 50 Earth masses of heavy elements, which is well above any of the planets in our solar system. Another object is this Uranus-Neptune analog. And for what it's worth, both of these were discovered with radio velocity. Transiting planets discovered by transits tend to be bigger. There's a bias there. Bigger signal, easier to discover. I wish we had nice pictures. Wish I had nice pictures to show you. Actual data of extrasolar planets. There'll be some images coming out soon which may be extrasolar planets, but they're nowhere near this pretty. This is one of my favorite systems, M-star, and it has 2 giant planets and a small, few Earth mass planet orbiting very close. Now, you can give a course. There's being a textbook written on extrasolar planets, but I don't have time to talk a lot about them. I just want to give you the key findings. And they're biased towards information about planets near the stars because the 2 methods which have been used for the overwhelming majority of detections are radio velocity and transits. Both are biased towards detecting planets near their stars and big planets. In the RV case, big as in massive. In the transit case, big as in large radius. But the 2 tend to go together. So about 1 in 150 Sun-like stars have planets more massive than Saturn within about a tenth of an AU. And most, if not all, of these are gas giants. We know that the transiting planets are gas giants. Models suggest that these planets formed further out and migrated inwards as a result of interactions probably with the disk out of which they formed. About 7% of Sun-like stars, and Sun-like means mass about 0.8 of a solar mass to maybe 1.2 solar masses. About 7% of Sun-like stars have planets more massive than Jupiter within about 2 AU, so they would be inside our asteroid belt. And many of these planets have eccentric orbits, many of the ones that aren't really close in and have orbits, orbital eccentricities which are tidally damped. Some stars are seen to have Jupiter-like companions, roughly a Jupiter mass, no giant planets orbiting inward, roughly the Jupiter position, nearly circular orbits. That's what I mean by Jupiter-like. At least a few percent. And maybe a few tens of percent. The majority don't. On the other hand, if a star had a Saturn in Jupiter's orbit and a Jupiter in Saturn's orbit, we wouldn't see any sign of it from radio velocities yet. There aren't many planets, I showed you that mass versus frequency observed, that are much more massive than Jupiter. And there are more giant planets around stars which have more heavy elements, that astronomers call metals. Okay, theory. This dates back a long time to scholars whose names are familiar to you for their philosophy and mathematics probably than for their astronomy. But thinkers had broader ranges there then. And these 18th century ideas haven't held sway continuously, but have been back in fashion, and we have strong evidence. Planets formed in a disk in orbit about the sun. And the reason that Kant and Laplace believed this were the coplanarity and near circularity of the planetary orbits. Now, disks are believed to form around most young stars, and that's the theory that I mentioned before of collapse over 5 orders of magnitude in size and conservation, roughly, of angular momentum from rotation. But that collapse over 5 orders of magnitude in size, we didn't know how stars formed. They didn't know how stars formed back in the 18th century. They did have an idea of conservation of angular momentum. And they certainly didn't have any observations of disks around young stars. But this is a model theory that predicts planet formation to be common, at least around single stars. With binary stars, the angular momentum could go into the angular momentum of the binary instead of the disk. There are other reasons to think. The disks have been seen in some binaries. There are suggestions that and some of the extrasolar planets have been seen in binaries. So we now have evidence for binary stars too. This is a little cartoon of what's going on. Material falls in to the planet, to the star and disk. Star actually has a wind throwing things off. This wasn't predicted before it was seen. It's kind of materials being fed in by the disk. It's a young star. Think of it just like a young child. Some of the food gets in its mouth and goes down, and some of it gets flung off in all sorts of directions. You end up with a disk. Planets form. The disk largely goes away, and you're left with a nice system like we have. Now, the idea of how planets form within that disk, dating back to Laplace, his ideas seem to be actually incorrect. And a different idea that was initiated by American geologist T.C. Chamberlain in the latter part of the 19th century is now believed to be the case. And Chamberlain didn't actually believe in a disk. He believed that a star came by, tugged out material, and that's how planetesimals form. But the idea is planets grow from little to big. You start with dust, you accrete, you agglomerate, and if you get big enough, the gravity can bring in gas. Stars form from big to little, collapse of things. If there's too much angular momentum, it'll split into multiple stars. Now, if you look at the mass distribution, it explains the planetary composition versus mass, because you start, it's just solid stuff, big stuff. You need gravity to bring the big stuff. It's general, depends how far you get, what you make, and it can count for the solar system, and there's a lot of diversity if you look at the models. There's a lot of stochasticity, even if there are just small changes in initial conditions. And if you look at different stars, they have different disks, so you'd expect large changes. A nice thing also, it explains, since planets form in a different way from stars, fundamentally different way, this explains why there's this big gap. You have actually that plot of planet mass versus number. If I went and continued it out to bigger sizes, that would be brown dwarfs, things that are too big to be planets but too small to be stars. And there are very few of them in orbit around sun-like stars. But then I continued it out even further into stars, stellar companions, binary stars. They're pretty common. And it would start going up. And that suggests fundamentally different mechanisms of formation of planets and stars. Here's a nice picture. Again, I'd like to have actual data, but this is an artist image of growth of a planet in a disk. And artistic license, you think of blue being cold, you know it's hot, but yeah. Okay. How do giant planets form? That's the subject of my talk. Well, there are three general models. The one that I'm focusing on is core nucleated accretion. Big rocks accumulate gas. It's this one unified model, as I just mentioned. Explains the composition of mass. Detailed models exist, and I'll tell you about one of those. And it takes millions of years, depending on the mass of the core and the atmospheric opacity. We're working on that. We think we can bring it down to around 1 million years, but depends on the mass of the core again. Another way is this fragmentation. During collapse, planets form like stars. It's rapid. Binary stars are common. But there's this mass gap that I just mentioned. It requires, for fragmentation, just because of how things cool off, you need cooling to have fragmentation. Most models suggest you need about 7 Jupiter masses or larger, and there aren't many giant planets that giant. And you need separate models for smaller bodies. No model for Uranus and Neptune. Violates Occam's razor. Occam's razor isn't always right, but it is an argument. Then there's this kind of intermediate model, giant gravitational instability. You have this disk, and it gets massive enough and cool enough that you get these clumps in the disk. And they condense to form the giant planets. You get the rapid growth because these occur on orbital timescales. But the problem is it takes a little longer for them to cool off. More severe problem is if you have a slightly unstable disk, you're going to have density waves and they're going to spread out the material in the disk. You need to get the disk very unstable on timescales faster than the density waves can act, which means you've got to either cool it off to make it thinner or add lots of mass to make more gravity, because those are the two things that makes more unstable. And it also has the same problem of doesn't work for solid bodies and really doesn't work for Uranus and Neptune, even though there have been 1 or 2 papers published suggesting that it might. But so this is the core nucleated instability model. You grow the core. There's solid line is solids, dotted line is gas, dot dash line is total. Core grows, very little gas. Gas comes in, radiates away energy, allows more gas to come in. When there's enough gas, then the planet just starts to compress under, the envelope compresses under its own weight. You add a lot more gas. And we just say, well, it's got to be truncated by a formation of a gap. But the older models, all the published models, actually haven't done this yet, the models of the giant planet formation. And the new stuff, which I'm going to be telling you about today, do show this. And what we're using, these are models. Other models have looked at the gas flow around planets. You get planets starting at Earth mass. You can't even see them in the disk. 3 Earth masses. You can see a little bit of a signal of them in this spot. 10 Earth masses, 30 Earth masses, now a Saturn mass. You're really seeing a gap starting to form, and a Jupiter mass, and you're not quite having a full gap. There's a gap around there, but the planet is still able to accrete somewhat. So, it's pre-existing models. The new stuff, models of Jupiter growth, incorporating both the hydrodynamic disk-related constraints that I mentioned, that I showed in the last slide, and the thermal constraints that I showed in the slide before, which prevent the planet from accepting the gas because the atmosphere just pushes out from thermal pressure. And these are the first models that really go from small bodies, we start around Mars mass for simplicity, to Jupiter mass. We do several different cases because we want to test different parameters. We don't know what the parameters are. They're not observed that well in protoplanetary disks. And this should be appearing on arXiv preprint server within a week or so. Just submitted. So what we do is we use some of Gennaro's calculations of the flow around the planets in the disks. And we look near the planet, and things are flowing by. These gold particles are flowing by. These are trajectories. These blue particles are staying near the planet. And this is just the initial positions of these same objects. This is a 10 Earth mass planet. And things stay around in about a radius of about a quarter of a Hill sphere around the planet. Actually, near the poles of the planet where the shear is less, some things outside of that region can stay. So the planet, really the stable region of gas held by the planet, is not spherical, but we can approximate it by that for our thermal calculations because we need detailed radiative transfer models, so we do these in 1D. Now, you saw earlier on the gas flow to the planet is limited by a gap. What is that gas flow? Well, if we look at it as a function of the mass of the planet, and this is one Jupiter mass here, Saturn mass here. These are funny units, but the key is where the peak occurs. At small masses, the planet just can't bring enough gas in. These aren't the thermal regions. These are just the flow limit, how much it can focus into itself. At large mass, it's clearing a gap. And it turns out, for this type of disk, it's around a Saturn mass. For this, it's around a third of a Saturn mass where the accretion rate peaks. And the difference between the two disks are viscosity. If you can think of it, if the disk is very viscous, it keeps filling in that gap, keeps flowing, dissipation causes things to flow. Whereas if there's low viscosity, the planet's able to push material away from itself and clear the gap. So in the high viscosity disk, the accretion rates can be higher, and they can peak, especially for planets around a Saturn mass and beyond. Things start dropping off at Jupiter mass here. That's the, let's see, that's 2 Jupiter masses is the last point, I think. Is that right, Gennaro? But they're dropping off significantly at Jupiter mass for the less viscous disk, and they're still pretty high at Jupiter mass for the more viscous disk. We've run several different models on these early stages. These are like the one that I showed you before, the Pollock et al. Results, but they have a little lower opacity and some other physics has been corrected. And there are various different models. They're very similar behavior, the solids, the gas, and the total. And they all have the same surface density of material in the disk. And that really just depends on that in this model. So there aren't much in the way of variations, a little difference in when things go. It's around 2.5 million years where rapid gas accretion occurs. Now the hydrodynamics aren't affecting things yet, but beyond that they do. That's the mass. This is the radius. The radius can be very large. The radius of the core is small and continually increases. The radius of the envelope is big. Jupiter's radius is around here. So in one case it gets up to around close to 100 Jupiter radii. In most cases it gets up to around 10. Big fluffy thing. Having to cool off so the gas can compress and more gas can come in. Cools off, shrinks, more gas can come in. And you see this rapid gas accretion is when it increases in the first part of it is when it increases in radius, and then there's so much gas it compresses because of its own weight. Here's the later stage growth in mass. There are different models. In some cases, it's just going to keep going, and we have to cut off its growth to make a Jupiter. But in some cases, if we have the lower viscosity disk and the planet having its, lower viscosity disk and the disk gradually losing material on a 3 million year time scale, can actually get a gradual reduction and end up with a Jupiter mass. And here are the planet's radius in some of those cases in those times where it's varying substantially during the rapid gas accretion. Luminosity, in some cases, peaks very high, but in all these cases, it peaks so high because we're letting things go very, very fast. In the case where it gradually tails off, this is actually not the luminosity, this is the integral of the luminosity, the total energy radiated. Luminosity never peaks nearly as high. It's more gradual amount of energy that's released. Now, I'm going to focus in, there's a whole bunch of cases. This is the most realistic case we believe we have. It's a lower viscosity disk. The disk dissipates on a 3 million year time scale, the gas. Mostly solids. Gas gradually comes in, gradually compresses, and then it accretes very quickly and then starts clearing a gap around itself. The disk is lost, and that's how you get the growth to these masses. And it's the hydrogen-helium mass is most of the total planet's mass, just a small amount of solid material. This is a logarithmic plot which shows the details a little differently, but it shows the details because the other one in the linear plot you're down near the bottom most of the time. But this really is what's going on. Planets down here. And these are kind of Uranus, Neptune type planets in this area. And then it quickly goes up to Jupiter mass. That may explain this suggested gap between Uranus and Neptune mass planets and Saturn mass planets. That there aren't too many of them because it goes through that phase fairly quickly. The radius of our best case planet, again, a little peak, but this ends up at about twice Jupiter's radius. It peaks at maybe, 40 or 50 Jupiter radii. Pretty big. Here's the luminosity. As I mentioned, it would peak in some of those cases where we arbitrarily cut it off, let it accrete really rapidly, was over 1% of a solar luminosity. This is a little over 10 to the minus 4 solar luminosities. And this luminosity is very important because observing these planets depend on this luminosity, the infrared luminosity. You have this earlier peak when there's the rapid accretion of solids, then it's gradually accreting gas and gradually cooling off and shrinking and allowing more gas to come in. This just shows the radius, where it peaks in radius when it's around a little under a Saturn mass, just because then it's starting to self-compress. Orbital evolution, you have interactions between the planets. I'll show you that. You have the system of nested orbits of planets. And see the orbits are getting close to one another as the colors are all the planets. The white circle is Jupiter's orbit. See that they're now starting to perturb one another much more substantially. And once they start really close scattering, then the system goes wild. And you can get very eccentric configurations. Now these orbits are crossing one another. They're not going to last much longer. You run the simulation for a little longer and you get a situation where you have very few planets left. In this case, you end up with just one single planet on an eccentric orbit. In the solar system, we've got things on circular orbits. We believe that the planets formed actually closer to one another than they are today, the giant planets. And they started to interact together. And Uranus and Neptune were tossed out to greater distances where their orbits were damped by interaction with much smaller bodies, most of which were thrown out, some of which were thrown out to the Oort cloud of comets, some of which remained in the Kuiper belt, which is another comet source. And you got much smaller eccentricities of the planets than we see in the case where you have the planets interacting when there's no dissipation. So anyway, I'll wrap up with this conclusion slide, and since it's a little after 1, I will let you read this during the question period. Thank you.
Hi, Jack, do you think there's any hope of identifying in our own solar system objects which may have been thrown out as distinct from what's in the, let's say, Kuiper belt today?
Well, we have scattered disk objects. Sedna, and various other objects were thrown out by the giant planets, presumably. The Oort cloud objects, which will eventually be seen, the bigger ones. Sedna could be viewed as an inner Oort cloud object. So in that case, yes. Of course, was something of Uranus-Neptune size thrown out into the Oort cloud? We don't know. It's possible. That would be very interesting to see. And as there are more all-sky surveys, maybe something like that will be seen.
In your Cornell model, you talked about fluid dynamic effects, but you didn't mention magnetic field. I was wondering, when do you set that in, and does it form shortly after the solid core, and would you expect it to affect the late kind of stages of gaseous secretion?
The gas fluid effects are not within the planet, but within the disk.
That's, yeah.
And magnetic fields, the disk may have magnetic fields. The sun's magnetic field substantially affects the protoplanetary disk nearby. The effect of the planet's magnetic field is probably not important on the material coming into the planet in bulk, but it may very well be important in terms of what the material that does get bound gravitationally to the planet, how that interacts, and therefore the formation of
that was my
planetary
question, whether
satellites.
you expected ambipolar diffusion and that kind of stuff.
Yeah. I don't know.
But that's not in the current.
It's not in the current model, but we're not following that subdisk anyway. So it's not relevant to the current model, which isn't to say it's not relevant to giant planet and satellite formation.
Right. So what you're saying is there's so much gas coming in.
That the flow, the magnetic field, any plausible magnetic field of one of these planets will not affect whether that gas falls into the planet's gravitational well. Now, it may be in this subdisk bound to the planet, and how it gets from that subdisk in. It's possible that you'd have a situation where the planet accretes gas from its subdisk later on when things aren't flowing in at incredible rates, in a manner like the star accretes from its disk where it's throwing things off. It's not accreting all of it. That would be interesting. But clearly, it has the largest potential for affecting satellite formation.